And then maybe after 5 or 7 minutes, I will say one important thing I want to share with you. So, can I have to control this way? Or can I control this way? So as you can see, the things I like is the moving. So this is on the right side, the water interaction with the air bubble, and then on the left side, the kind of particle simulations, the smoke filling the space, and how it is interacting into the space and the particles. The next thing is one of state of the art in the CFD, and you will see what's going on here. Let's prepare some of the video. On the right, on the top, that is an electric spark, and then the the lines are moving, and at some point we can compute the highly probable point of the spark initially started. So energy is released into the space, and then so the things you're looking at right now, the flame structures are propagated in your gasoline engines. Actually, this is the proper prototype of the BMW engine, and then the mesh is moving, as you can see, going downwards, and then the flame is propagated into space. And then the next one is it's the image processing, and then I think some of you already noticed who he is on the screen. And then he was my old colleague in my PhD. And then you can see some of the speckles on the image, and depending on the resolutions of the projector. But if I change the screen, if I change the data set as a just graphical function in the gray image, and you can see really like a very noisy type of things. And this can be easily removed by using some of the PDE structure. And then there's a clean surface. And this is image demo. And we can go further, like a more extreme case, some kind of image. Even we cannot notice what it looks like. By using the energy minimization on the left side, we can actually recover the image, what is behind. And we can even go further on the red cells, sorry about the colors. And then on the red cells, we have no idea what's going on, but we can still recover from the known information, and then it is actually a lotus flower. And another example, we are moving into the computer vision, and then same guy making the front face, but the whole simulation is done like a beginning of the image and the end of the image. In the middle, we're interpolating somehow by using the energy minimization. So you can see like lots of energy minimization is happening here. And another example, the very cheesy drawing, what I drew myself at a time ago. And then we want to make it pop up the surface like a graphical function like that. So how we can do this? And then again, the energy minimization. And then nowadays, these type of things are very easy to solve it by using the machine learning nature, because we have lots of data. But all of these things, we didn't do anything machine learning. Just given data set, energy minimization, that was it. So we extend the idea, another extreme case, and it's a kind of machine learning, but we didn't use anything data set. It's from the point cloud, we want to recover the surface like that, inside and outside. And another examples of the surface reconstructions from the point cloud, you probably can notice what it is. And it's actually a car. And then the difference is the surface reconstruction, as you see on the dragon and this one, actually we can recover all the inside shape. So it's topologically different layers of inside, and then we recover the distance function, and then from then we can recover the surface. So you may wonder why I'm talking about this type of diverse examples. So that was like a wrap-up of the research of around 15 years. But in the meantime, the thing what I struggle the most is to deal with the noise. I didn't say anything about noise. I mean, you already saw some of the examples of denoising the images. But actually, some other examples, even for the beginning of the CFD examples or some other simulations, solving the partial differential equations. And nowadays, whenever we need to deal with the data, and noise is the thing you cannot avoid. And then 2 years ago, actually, I found very nice literature, which is the topological data analysis. And I found it, I immediately noticed that that is the most robust method against noise. So I just immediately felt it like, wow, this is really amazing, and I want to do something. And then I met these guys, fantastic guys, the 3 postdocs on the top, and then 3 professors. And then they are also very enthusiastic of doing the research in many different directions. So I introduced them the topological data analysis, what you can do. So we made the collaborations. And then the first example I want to share with you is the chromatography. And it's not just a chromatography, it's a 2-dimensional gas chromatography with a high resolution mass spectrum. But I think you already know what is the chromatography. No? So I wrote this. So it's like your childhood experimental thing to see the separations of the colors through the paper, and then see the black point has the separations of the different colors, and then black is not just black, it's a combination of the different colors. But we want to do it the same concept, same thing for the gas phase through the 2 different pipes. The separation is not happening just one pipe, it's happening from the 1 and then 2nd pipe. The reason why we need to do these second separations because the signals A and B is indistinguishable, but actually the A is consists of these signals and B is consists of the other signals, so we can see the more details of the separations of the gas phase. And that's the machine why we are using it. And I'm not using it by myself, but my collaborators in analytic chemistry, they are using this fancy machine, LECO, I think it's an American company now. So inside of the machine, we have 2 coils, and that is the sample comes in, and it's actually there is a liquid phase, but they evaporate the samples, and then the gas phase is going into the pipe, and through the pipe, the one chemical compound by one chemical compound is coming out on that side, and then there is one electron hit that chemical compound, and that chemical compound is destroyed, and through the electromagnetic wave, the field, and then all the particles are spread out into the space, and then we measure that the distances or strengths of destroyed chemical compounds. So that is a usual output from the machine, and then they have also software. We can see this diagram. I will get back this diagram anyway, sooner or later. But now it's time to see what we are measuring of this fancy, expensive experimental thing. Actually, why? Yeah, I think yesterday I was thinking about buy a couple of bottles of wine and then, while you're drinking and then listening at the same time. But I think in a Korean institute, maybe it's a different thing.
I have 2 bottles in my room now.
Yeah. But it's not just all kinds of wine. We are especially interested with botrytized wine, if you know what it is. You may have heard Tokai wine, maybe sweet wine. It is one kind of wine, botrytized wine. It has a very depth sweetness and different types of taste. But of course, to characterize wine, we have many different ways, like looking at color and flavor, and we also have a special people, sommelier, to see the characters of the wine. And my way is, of course, the tasting. But here, they measure this wine and then obtain this data set, and then first and second time, and then in each point in this diagram, there is a mass spectrum signals. So every single point here, roughly 500,000 points, and every single point has a function.
So what is X and Y axis?
X and then first time step, and then the first separation and the second separation. there are two coils inside.
What I mean is the x-axis. Is there any meaning in this x-axis value?
Yeah, it's a time. It's basically time.
Time.
Yeah, it's an actual physical time, and then another time step, another time dimension. So they have two different times. I mean, actually, it's a lexicographic order, so it's actually one dimension like this. But they want to present it this way.
After time, we measure the sum inside the component and then perform the mass spec.
Yeah, exactly. So it's a mass spec, and the mass spectra can be understood as a continuous function, but it looks like a very spiky function, but it's like a continuous function. But dealing with the continuous function is not easy, so we have to discretize it. I mean, that's what we had it from our education purpose, and then see we discretize this continuous signal, and then we just embed this continuous signal into the like a fixed dimensional space. And in the case of quite large space, and then the integer coordinate or integer coordinate, we select the sum of the signals. And then color means here actually the sum of the signals, and then make the from the small value to the large value, and then we rescale it, and then from the blue to red. Yeah, that's the basic information we have. So I think everyone understands now. So many points. For each point, we have a 500-dimensional vector. So it's like a tensor kind of data. And an interesting thing of this data set is from the chemistry. If you multiply the mass spectra constant times, actually this is the same chemical compound. The difference is basically different amounts. But since we want to see not an amount, but the different types of the chemical compounds, actually we can use this very nice property of differential relation. Constant times is every constant times of the vector is the same, which means we can make a quotient space. So from the large dimension, we normalize it, and we obtain normalized vector. So every vector now stays on the sphere. So the question we want to ask, how can we see the differences between the wines, right? But this is a really easy question. So you can do the PCA, just doing some of the very simple manipulation of the data set. We can already see the differences, very nice diagrams of different labels and different groups of the wine. So we brought this result to the chemist, and then they said, yeah, maybe this is not what we want. So it's like every time it's a different communications or different levels of something. I mean, they already got this result, but they want to know what makes differences. So which chemical compounds do you have makes the differences from one group of wine and then the other group of wine. Meaning is, we have to go back to the original data set to compare everything. Then we can make the differences, right? So the next step, what is the proper metric? And metric here is, of course, the right metric. We have to see the angle differences. That's the correct metric in a high-dimensional sphere. But using that amount of data and then measuring all the distances with the cosine dissimilarities or angle differences, you have to compute the cosine inverse. Takes a lot of time. I mean, we can do the analysis like 1 or 2 days. This is okay. But I don't have that kind of patience to wait the computing results very long time. So I just ended up to use the very simple Euclidean distance. You may think it is not a great idea, but thinking about that amount of dimension, and all the coordinates here are positive values, the meaning is huge dimension. You're looking at very wedgy kind of shape only on the sphere. So that and that, very similar. Okay, so still we have so many data sets, and it just bugs me a lot all the time. And the easiest way to do it is like using the dimension reduction. And I wanted to show you some examples why I'm doing the dimension reduction at all in this case. Using this level of dimension reduction doesn't make sense because we want to pick up some of the chemical compounds to make the differences. So we have to do the dimension reduction. We can do it in this way. If I reduce this one, k dimension, into the 2 dimension, it's like a 2 coordinates, so we can actually visualize this amount of data point on 2 dimensions. So I brought the example, and actually same color. The blue here is a blue here, and red here is one of the red here. This is the result of the PCA. And what you can see, everything's distorted, and everything's overlapped. So it's not that nice, right? Looks nice, but we cannot do anything for it. Disney also looks nice, but if you want to do something else extra, you need to do the the clustering, and the clustering in this way, and YCK. What is the number of clusters which I have to decide? This is like a big question. I don't know how to do it. But some of our great ideas he presented this morning, and nice ideas. But also the MDS doesn't work because of a memory problem, and UMAP does not show anything better results. But using the ball mapper, which I'm going to explain to you like in a few minutes, and this ball mapper can present very nice graph structures, and all the reds and then green and blue. I mean, it's like an overlap somehow, but actually this is line by line. It's a very like a spiky structure, and then you can see quite a good differentiations of the red and blue and green. So I brought another example, same problem, but ball mapper already show you a different result of the graph. So it's really exciting because you have a huge demand, a huge number of points, and then you reduce it, and then present it as a graph, and it looks quite different. So I was really excited. Then I was trying to search all these heavy research topics in the last 20 years of the graph theory, and then I also asked to many smart people in the graph theory, but their interest is quite different from mine. So I think that for the next step of the research, I want to do something more graph-oriented research, but unfortunately, at this time, we only used the ball mapper, and then we didn't use the nice structures of the graph, especially edge. We didn't use anything. So what is the ball mapper? Ball mapper is one of the TDA tool to visualize high-dimensional data into the graph. And I strongly recommend this YouTube, and then the creator of the ball mapper, and he made a very nice lecture, I think 40 minutes, and a very funny dude. And so this guy is one of the guy on the screen.
Sir, can I ask a quick question?
Sure.
I missed some part. If we have one simulation, for example, we have one Y, for example, then we can get that ball map from the one Y.
Yes.
Is it right?
Yeah. Yeah. So that was already the second one.
Yeah, right. There's the first one and the
Second one. Thank you. Yeah. Sometimes cannot follow all the details, but thank you so much. So if you have any questions in the middle, just stop me.
Can I ask one?
Yeah, sure.
If that is from wine, then that means, can I think as some property of wine, for example, taste and smell like that?
Oh, this is another good question. In this machine, since we are using the gas phase, I think the taste, acidity, and it cannot be distinguishable, but the aroma can be detected. So the main research of this one to find out the hidden aroma, what is the chemical compounds to make that specific aroma.
Thank you.
But unfortunately, they cannot check 500,000 points because it's so many. Ball mapper, each point here, you may think this is a 5-dimensional point, but I just plotted in a 2D. And how ball mapper works are very simple. We choose the one point, random point, and then make the epsilon ball, and then treat them as the same point. So this one big ball, epsilon ball, is the one node in the graph. And we move to the next point, random choice, or in a table for the next point, and then choose the next one. And the next one, eventually, it can be covered as an epsilon ball. So we are creating the epsilon cover of the data point. And then the next one is much simpler to connect them as edges. Whenever they have an overlap between the balls, they check it and then make a graph. So that was the result of this diagram. from 500,000 points, we can reduce around the 1,000 points, maybe 700, maybe 1,200, depending on the size of the data and depending on the structures of the lines, mass spectra. And the reason why I use this epsilon 0.08 is actually from the experimental thing, because they have data of measuring the same line twice. So we can easily check it, what is the a threshold value to cover most of the similar things. And epsilon 0.08 covering like a 95% is the same value. So I think this is a kind of reasonable choice. And using this choice, we can reduce a lot of them. And then, yes.
So when you make the bowl, do you have overlap between the bowls?
Yes.
So how can you deal with that? So you can make the, you can decide the, so how can we decide the number of points?
We need to search it. Yeah. They are measuring the distance. I mean, it takes time in the beginning. They comparing the distances, and then in the epsilon ball. So you have a distance metric, in this case a Euclidean metric, and then check the metric, and then it's actually the epsilon ball in the metric space, in the Rn space.
Okay.
So whenever these two balls are overlapped, we draw one edge here. So we treat the center of balls can be very representative mass spectra from the 500,000 mass spectra.
So here, what color represents?
The color, good question. Color is the same color here. Yeah, basically each point, the color here is the summation of the mass spectra. And then here, basically this ball contains maybe some of the mass spectra. We average them. So it's a very similar colors. The red here, the very dark red, is probably this point. Yeah. So we treat them, the central balls, as a representative mass spectra of the one line. So from the 500,000, we reduce the 1,000 roughly. And then the next thing is a bit philosophical question by myself. Like, how can you say you're the unique one in the world? So if I exist myself in the world, I'm unique because there is no one else. But if there are some people out there, I mean, I don't want to compare them, but I have to say what is the unique features by myself to see other people. And this guy is a good at for something else. I'm good at for the other thing, and that makes you as a unique person in the world. So choose the one point, and I want to say that is the unique point comparing to other ones. And how can I do it? Just compare them all. Let's bring all the lines here and measure the distance, which is more than 3 delta, and then eventually that one, all the inside of the chemical compounds has the distance more than delta. The easy way. Then this mass spectra is really the unique one, which has the certain distance comparing to all other ones. Right? So up to now, what we have done so far, from the 34 lines, we found relatively unique mass spectra around 2,700. But this is just random points right now. Right? 2,700 points in the 500 dimension, just randomly distributed somewhere. And then the question is, how can I see the distribution of these points? And then you already know the answer, and then we can use the whole map again with a bit larger distance, and then that's the result we have. So in each node here contains a different amount of mass spectra from the 2,792, but not all of them, some of them, but we can actually trace down where they come from. So this mass spectra is coming from Gaussian line. Actually, we count them and then measuring them from the white to red, the ratio. And the red means basically that contains all the mass spectra from the Gaussian line, and the white means is basically nothing from the Gaussian line.
What is the size of the book?
Very good questions. number of points.
Size.
Yeah. So it's a bigger point, a bigger radius. Actually, this contains more points, more mass spectra in this case. So that's the Austrian wine, and then I will switch the Hungarian wine, and then just try to see what the difference is. And that's Hungary. It's a bit different, isn't it? And then Austria and Hungary. So I don't know what they are, but it makes some differences. But in the middle is like a very common part. And then I will switch to the Slovak wine. That's it. It has basically more overlap comparing to Hungarian Austrian. Between the Slovak and Hungary has a more overlap. I will get back to this point sooner or later. But still, the Slovak wine has some features on the different players. And that's the last one, the French one. And obviously, French wine is on the other island. And then probably you don't understand the joke here. Okay, never mind. And then this is the status what we have it. For 34 wines, we select very unique mass spectra, relatively unique mass spectra, which is roughly 2,700. 2,700. And then I just visualize this chaotic number of points in the very nice diagram. And how many of you are familiar with the TDA method?
I think there should be someone who don't know.
Okay. Then I will just keep it, and if I need it, I will get back to this point. And there's this. So ball mapper is the one type of mapper which was used in the topological data analysis. But originally, there is a very nice concept of creating the similar graph, but it's a very different concept. Okay. So if I need it, I will get back to this point. So for now, we have a different number of points. 2,700. So the question here, we visualize it as a one diagram, which we already see. We already saw the Austrian, Hungarian, Slovak, and French. But the thing is, you probably noticed that using the ball mapper to create the graph, it is dependent on how to choose the first element, right? If I change the first element in a different location, the shape of the graph will be slightly changed, or even it can be changed quite abruptly. So that is the main reason ball mapper is not really commonly used in the TDA community. Because they literally do not like to this type of instability. But I can see the infinite possibility. Why? Because you choose the one element, starting from one view, and then create one ball mapper graph. And from this ball mapper graph, you can easily change it to the frequency matrix, so different types of lines, different nodes, and then we can check how many Austrian lines are contained in which node, so one frequency matrix. And if I change the viewpoint, meaning is starting with a different point, and I can create another matrix, another matrix, another matrix, up to 1,000. You can create a 10,000, which means you are looking at a high-dimensional data point cloud in 1,000 different viewpoints. So how can I understand the high-dimensional data set in one single view? That is the classical TDA mapper. The ball mapper can create very different multi-view of understanding high-dimensional data sets. But the problem is, we have a matrix now, and how can we summarize this data set into the one understanding nature? And then we know many techniques actually. So from each matrix, we run the hierarchical clustering, but in the hierarchical clustering, we need to choose the number of components, of course, and then we just check from the 2 to 15, and then because we have 34 wines, and then 15 is not the small number of the clusters, and then we check this the quality of the clustering by using the RE number, and this actually shows the consistently reliable grouping, and if it is more than 0.5, it's a really reliable, and then we check them all, if we found it maximum value is 11, And I think if we choose the 11, we can select, I think, more than 980 matrices over 1,000. So that was quite an optimal number we can choose it. So the situation right now, we randomly choose 1,000 matrices. And then we found that the number 11 is a very optimal number of the clustering. And then we choose this number, and then doing the clustering 980 matrices. So you have a 980 clustering results. And then probably the next thing is very natural. You want to see how many same clusterings are happening in the 980 groups. And we used a very rough algorithm, and we found it, the final result. So that is a one node. One node here is meaning it's a one cluster, and then this cluster was observed 979 times and 989 at 6 times. So quite a diverse number of points are observed. But the interesting thing is the labels of the green Augsburg is from Austria, and Toka is from Hungary and Slovak, and then difficult to pronounce this one. Sultan, the French. Afraid of pronouncing the French. So the yellow is a French wine. So you can see some diverse connections, and I can even go into the details of the Slovakia and Hungary different labels, and then see the Hungarian wines are quite similar to the Slovak wine, but you have some unique features of the Hungarian wine, and the Slovak wine is here. That is your that result I already showed you. In the overlapping way, the Slovak and Hungarian wines are more common factors comparing to others. Actually, it's from the geographical reason, because they produced the wine together a long time ago from the Hungarian Austrian Empire. And in Austria, they developed some new techniques, and then they found it more like a diverse natures of the wine tasting, and then that's the reason they have a unique features. And the French is already quite different, far away. And then we can even go into the detail of the different winery even, and then the Benzel, quite a very unique features here. And at that point, we can actually answer the question which I already asked you, what makes the differences from one wine to the other wine? We already select the unique features of the mass spectra, and that mass spectra just brings this diagram, and then you can see the differences. And then the remaining thing is the chemist, the analytic chemist, found some interesting observations from this 2,792 unique mass spectra. They found it roughly more than 1,000 really the known chemical compounds, and among them they found it 334 compounds, which is related to the aroma. And then you may think, starting from 500,000, that is a really small number of points. But previous literature, they only found, I think, 40 or something. But in this case, we just reducing the epsilon, and we can actually find more. And this, from the 2,000 to the 1,191, that is actually the human work. Everyone needs to sit down and they check by their methodologies, and then one by one, which one makes sense and which one does not make sense. It is like a very critical area, which I can explain right now. Any questions so far?
I think it's a good time to ask a question for the first part, and then we can move for the next topic. So, any question, please feel free to.
So basically you made a multiple ball mapper, and you use the instability of that ball mapper to find the most consensus output, right?
Yeah.
But you are not using the edge information.
Edge information is missed. Yeah. If you can use edge information, that might be very interesting. I mean, the question we had it from our side, and then we wanted to trace down what's happening for the chemical properties of maybe this line. Actually, we can trace down, just select a few of them, and then ask to the chemist what's happening there. That might be an interesting question. Yeah. Too boring? Yeah, please.
Depending on the definition of distance between two endpoints, can we have different type of data collection
Yeah. So it really depends on your choice of the metric of the space. Yeah. I think the Python code, you can add your own definition of the metric. You can send over that function into the Python code in the ball mapper, and then it's just code for it. But of course, in this case, it takes time. The reason I choose the Euclidean distance is the fastest one. Yes, please.
So here you choose epsilon by using some chemical knowledge. So is there any method that to find some appropriate epsilon from data, only data?
Yes, that's a very good question. And then the next thing I didn't do it, but there's a huge ball here. It contains so many points, and then they wanted to make a very evenly distributions, even density for each node. So when you search it, you just make them choosing the different epsilon even, or fix the epsilon, but make the something even number of points inside the ball. So that might be only knowledge I can say. Yeah. But those things are actually correlated to the pre-knowledge what you want to do. Yeah. If you want to make the even distribution, you can do it that way. Yeah. Yes, please.
Sorry, I'm confused about the data here.
Okay.
Can you just summarize what is the dimension and what is the data point, the number of data points?
Oh yes, please. So this is a
this one figure is from 1 point.
yes. One figure is 1 point. 1 7.
But we have 34.
34 diagrams.
And 1 point represents 1 point.
1 point in this figure, which is a T1, T2. The separation time. For each point, we have a vector, or we have a function. So that is
500.
exactly.
And we reduce 500 to make it 2.
No.
I think so.
Reduce the number. The dimension still stays. Okay.
I see.
This guy contains 500 meter as but it's drawn as a 2. This is a graph.
How can we interpret each point?
Good question. Each mass spectra is the fingerprint of the chemical compound. Yeah. So technically, they should know what it is, but it's not always. That's the reason we found it 2,700, but we ended up to have only 1,192 known chemical compounds.
Kind of the center of all that blue mass, maybe you can think as all some common compound across all the.
Yes.
Yeah. Yes.
Yeah.
Yes.
Yeah. So it's exact. Like in the middle here, the middle part is very densely populated, and then they are always like a similar kind of spectrum
Across the whole graph.
Yeah. I mean, that is very natural. So how wine can be so much different from one wine to the other wine? Or the alcohol. And,
Kind of it would be very ideal that every branch corresponding to the single one. Then if we really ideal, maybe every branch could be corresponding to one different one. Then this whole map would be amazing. I don't know.
yeah, it could be.
Yeah.
I think it's a really nice visualization tool. You can use it for the high dimensional data, and you can feel it like even before doing the analysis. You can feel it. Oh, maybe this is different from one to the other, and then you can actually map the color by using the user function, and then it depends on what kind of data you have. Usually, it's metadata. So if you have a metadata, you can map it to see how it interpreted. Yeah, please.
More questions. So here, and this color means that each ball has many single point
Yes.
here. Then this color represents each point in the ball.
I average it.
Average.
Yeah, I agree. In this case, the ball contains different mass spectra in a different country. I highlight them only from Hungary.
Okay.
So this one, no Hungarian.
Oh, I see.
So no mass spectra from Hungary. The red means all of them is from America.
And, when you apply this ball method, so when you draw the ball, you need to choose the center. How do you choose this?
I think this algorithm already select the center and then draw the epsilon ball and then check the distance nearby. And then, so they call it landmark. I don't like the name, but
That the randomness comes from how
yes, how we started, and then how the matrices are. I mean, then the question. I will get back to you. Just give me a second. And then the randomness is coming from the selections of the points. But then you may have a questions in the beginning. Why I didn't check the randomness here, right? But in this case, here's a time dimension. The time dimensions already gives you the order of the feature matrix. So I shouldn't like make the bigger like a mix of this order because the time dimension is already fixed dimension for the order line. But after we select the unique one, actually time dimension is gone. Then I have to think about the instability. Please.
Yes. I have a question regarding actually the ball mapper algorithm. So basically, you select a point randomly, you draw a sphere around it, and then you connect all the spheres depending on their overlap. But one sphere can contain more than one, contains several points, and each sphere can contain different numbers of points. So how do we determine the number of points for each sphere actually?
I have to this algorithm measure all the distances to the other points, and then the meaning is the distance. You can check whether it is larger than epsilon or smaller than epsilon. If it is smaller than epsilon, this is all the points inside of the ball.
Oh.
Yeah. So it takes time. But there are some ways we can improve the computational thing using the parallel algorithm, which I didn't do it here in this case, because I don't need to use the smaller than this number. If I need to use the smaller this number, and it takes a lot of time to compute it, because the structure of the ball method can be complicated. Any other questions?
If we add a little bit noise into the data,
Yes.
how much this ball map to make sense?
Very robust.
Very robust.
Very robust. That's the key point. Because you cover the epsilon ball as they are. I mean, if the noise is too large, of course, it makes a problem. But it's like a small types of noise. It's quite.
So yeah, what do you think? Do you think this ball map can be used for single cell RNA?
Yeah, I think the generating ball mapping is
Anyway,
kind of grouping the features.
Yes, exactly.
So
It's actually giving you the micro clustering somehow.
yeah.
Yeah.
And after generating ball mapping, you just use the that group information contained in that group grouped marker. But if I apply this method on the single cell RNA sequencing data, I would like to find the relationship between the markers.
Yeah, of course we can do it actually. So all the data points are related. I mean, it's a good question anyway. Relationship and edges and so on. Yeah. But in the morning, what I said is reducing the epsilon complicated, very complicated structures of ball map graph, and then actually you can aggregate it of the map graph using the partial
So
differential
you can apply another cluster.
Yeah, exactly.
Feature.
I think we can move on.
Yeah.
But I think the run out of the time.
It's okay. No problem.
Okay. Thank you. Okay. So this is the second topic what I want to share with you, but I will make it quick because if I go into the details, it's too complicated. So I will do my best to simplify everything. But it's a kind of irony thing. We talked about wine, the most dangerous drink to cause some cancer, but we are going to talk about the cancer now. Kind of irony I found it for preparation of this talk. So this case, we need to talk about topological data analysis a bit more. And then TDA, in this case, can bring you some of this olive color of the diagrams. I will explain to you what it is. So data perspective. We have 78 patients in the diffuse large B-cell lymphoma, one kind of cancer. And we have 97 images. But these images are selected by the oncologist without any prior knowledge and nothing else. They just selected interesting points. So each patient have a different number of images. Maybe one patient has 20 images, one patient have maybe 5 images. So there is a huge discrepancy of the images per patient. And then using some other techniques, which is the inform software. So this is a stained image, I didn't explain it to you. Multiplex immunofluorescence imaging from the biopsy, and then they do this coloring thing on the staining things on the proteins and then of these cells and different types of cells here. And so that's the reason they have different colors. And then through this software, Inform, they can actually make a phenotyping, but phenotyping of the result. So all the colors are all the, I think that is the malignant cells, and all the different colors are immune cells. But as you already know, in this group, the accuracy of this data set of the phenotyping is very poor. So we cannot believe that is actually the cancer cell or not. There is we hope that is a belief. So we use it in this study. We believe you guys 100%, and then that is a cancer cell, and then that is the immune cells. Why we want to do it? So this data set is annotated by the oncologist, in the middle of the cancer area, or some of the boundary or border of the cancer areas. So this is olive colors, and there is many different colors, meaning it's different phenotypes of the immune cells. What we want to do it to look for some explainable the spatial correlations between the cancer cell, the malignant cells, and the immune cells. That is the spatial correlations we want to find. And then the second question is basically, quantifying the relation. But in order to quantify the relations, we need to know how we can analyze, how we can extract some of the information from this point cloud. So TDA in 2 minutes. You growing the epsilon ball, it is increasing. So at some point, you can see the 2 connected components of these blue things, and then this will be disappeared when the epsilon goes larger and larger. At that point, it is died, right? The 2 connected components, actually the several connected components are started from here. That's the reason we have some of the diagrams. And then actually this birth and death explains the epsilon, the radius, and then this radius is growing. At some point, it will be dead, right? And I also recommend to read this medium.com data science, and he wrote excellent introductions of understanding TDA. And the next thing, instead of checking the connected component, we want to check the H1 structure, meaning is how many circles you have it. So at some point, this is one circle, but epsilon grows and grows, and then the circles collapse down, and now it's a single component. So this H1 structure is gone, and then we will see one more time. So there are so many circles and holes, and it explains some of the data set here. At some point, so then I think this is here. The meaning is on the radius 0.3, the big circle started, but that one is gone when the radius is 0.7. So it's quite understandable, right? So that is the way they extract the simplest or complex structures of growing the circles from the point cloud. So we will use the same concept for this point cloud. And then the density difference is 4 times. And then we can still select one of these light blue points, which contains the longest structures of H1, which is a circular shape. And then we pick the point And we want to see what is the shape of the simplex, which is the triangles and lines, and then map it here again. So it's not always like there is empty surface for sure, but this big structure is almost the same from the top and bottom. But think about the level of the noise here is like a really devastating. But we can still find kind of donut shape of things just looking at the persistent diagram. So using the same technique, I will just flip the screen one more time. If you look at the clear olive points in the next screen, it's the shape of malignant cells. Like this. See? You probably cannot notice there is a hole here, but in the next screen, you can see some of the holes, the very empty space here, And then, of course, it doesn't matter the point cloud distributions. You can also use it in this complicated example. Actually, the main reason we started this research is because of pancreatic cancer, which is another devastating, very dangerous cancer. But we couldn't get all the data set at point. But this lymphoma data is already online, so we use that lymphoma data. So you can see this pink shade. There are many holes. Actually, these holes explain some of the blood vessels through the pancreatic organ. And then around this point, the red points are close by, and then they want to see some correlations between these points. So the first step, you have to extract the global shape of the point cloud. So that was it. And then I just map another phenotype on top of this olive triangles. And then we call it in the beginning is a cancer island, but it's a very cheesy name. So we choose to name it like a topological malignant cells or regions. And actually it's like an area. And then why this area is very important? Because you can see some of these immune cells are outside of the cancer area, or some of them actually inside. Which means we can explain the infiltrations to the cancer cells in a very mechanical way. How we can measure the distance, of course. And this is another use. But looking at these two diagrams, we made the examples. On the right side is a very high density, on the left side is not that high density, but it's ended up to have a very similar diagrams. The meaning is if you're standing here, it should be different, right? Because you're surrounded by so many cancer cells, you're surrounded by some of the sparse cancer cells. Then the next concept we can think of density, right? So we add the density profile from this point cloud, and then measure the density from immune cells to the cancer cells. From one diagram, these color things are immune cells, and we can measure the distance to the island. Actually, we can find the distance. That was my topic for last 5 years. Compute the distances like this. And then we can also compute the density. We can make two different values in different diagrams. This distance versus density of that immune cell. So we can see the correlations very nicely of the different immune cells and different immune cells. And now this is the image from in the middle of the cancer area. And if you're standing in the border area, the diagrams are quite different. So we have a very different features, and we like that. But the thing is that it's a different types of point cloud, and then we need to summarize these things to grab the features in a different way. And then I actually ran out all the ideas, nice ideas, so I just ended up to use the PCA. Why? It's two-dimensional. I'm not doing anything dimensional, but I can see the distribution of the point clouds. So PCA 1 and 2, and then the mean values of the distance and the mean value of the density. We can extract these 6-dimensional vectors of each immune cell, 3 different types. So we ended up to have 18-dimensional features for each image. So we have 900 images, and then for each image, we extract 18-dimensional vector, which already explains the distribution relationship between the cancer cells and the immune cells. And the next step, of course, we want to see the diagrams. And Tisney and UMAP shows you very nice diagram. I think many people will be very happy to see this type of diagram because we have a very clear, distinguishable diagrams of these 18-dimensional features of 900 images. But then what? What do you want to do afterwards? It's a kind of strange. I mean, it's a nice diagram, but that's it. I mean, there's no further things. I mean, we want to connect the patient, we want to connect something else. Then I think the ball mapper can give you a chance to see the correlations between the images. So we draw the ball mapper, and this is the diagram of the ball mapper. And in this case, I make a color from the image. We can count number of images from the cancer, middle of the cancer, or border of the cancers. And then the red contains all the way from the middle of the cancers, and the blue means from the border of cancers. So in this diagram, you can see very nice flavors. So upwards, and here is many border images. Then actually now you have a chance to connect the patient data, right? How? We again, like doing lots of inspections, lots of tests, viewing the same high-dimensional data in different views, and then connect to the patient data and to see the correlate the patient the survival rate. Why it is important? Because we can also correlate different things here. The first component of eigenvector, and then this means it's a positive and negative. Meaning is that side, the negative means your immune cells are infiltrated more towards the cancer, and this one positive means that immune cells are out quite far away from the cancer cells. So it already explains the geometrical meanings of the relations between these immune and cancer cells, malignant cells. So I'm not going into the details, so I just made one big diagram. That's the procedures we had it. And then now from here, we do the same thing, like a shuffling of the matrix and doing the hierarchical clustering analysis and finding the optimal number of clusters in many different ways. And linked to the K-man analysis, we found it what is the poor and good survival rate and see the differences. So maybe I should be able to explain all the details more and more, but I'm not that expert in this topic. But the one thing I can say that if the patient have more border images, and then they have a better survival. But that makes sense because the border image, if the patient has the border images, which means it's not all of the middle of the cancer, it is observed. There is some borderlines of the cancers and then the normal immune cells, but not all of them. And then this TR, the middle of cancer, and then middle of cancer and border of cancers, have so many different interactions patterns. So we just decided to divide it into these two things and then make the analysis in a different way. So I will just skip this one. But there's an archive paper, so you can check it what's going on. And then the last thing, only for the border images, but not all the border images explains to you the better survival. If you check the poor survival rate, poor survival patient who has the border images, actually that is very close pattern to the cancer, to the middle of the cancer images. It has the very similar patterns. So it looks like a border, but it has the patterns of the cancer. That is a kind of a striking point of looking at the data and finding all the details. So I have one take-home message today. Thank you so much for your patience, for listening all the time. And then this take-home message is very simple. I believe it. I think you can correlate with some other data set, and for your analysis of the data, and then I think you can do better. Thank you so much.
Yeah, please, feel free to have a question.